Hi there, and welcome to this lesson on Further Pure Mathematics 3. In this lesson, we're on Chapter 1, 1.3, and inverse hyperbolic functions. First of all, we'll be looking at how you sketch them, and then we'll be having a look at the formulas for working out inverse hyperbolic functions. The easiest way to sketch them is to reflect the corresponding graph of the hyperbolic function in the line y equals x. So for example, if y equals sine x, first of all, the inverse function is called r sine x, or you may see arc sine x. Either notation is fine. Sine x looks like that. There's the line y equals x, and we just need to reflect the curve in the line. I'll let you have a go at doing that. So pause the video, do a quick sketch, and then come back to me. Okay, let's have a look. So if I reflect sine x in the line y equals x, I should get something that looks a little bit like that. We'll do the same thing for cos x. The inverse function is called r cos x. That's what cos x looks like. And there's the line y equals x. So I just need to reflect the curve in that line. Now, there is an issue this time with the inverse function. You may or may not spot it. But anyway, I'll let you have a go at doing this yourself first. So pause the video and then come back to me when you're ready. Okay, let's have a look. So reflecting the curve in the line y equals x does give me that. The issue here is to do with the definition of functions, which is that a function should not be one to many. That means if I put in any value of x, I should only get one value for y out of the function. Graphically, it means I shouldn't be able to draw a vertical line that cuts through the curve twice, which I clearly can do here. Now, the way we deal with that problem is we limit the domain of the original function. So we limit the domain of y equals cos x to x has to be greater than or equal to 0. And that just gives us 1/2 of the curve, which means we only get 1/2 when we reflect it in the line y equals x. So that's what the inverse function would look like. For tan x, the inverse function is called r tan x. That's what tan x looks like. Now, it's a little bit more fiddly, this one. If you're going to reflect that in the line y equals x, first of all, I would reflect the two asymptotes, and then I would reflect the curve. Anyway, I'll let you have a go at doing it yourself first. So pause the video, have a go, and then come back to me when you're ready. Okay, let's have a look. Now, as I said, I would reflect these two horizontal asymptotes first, and they become vertical asymptotes at plus or minus 1. Then I would reflect the curve, which will go somewhere like that. So that's the curve y equals r tan x, the inverse of tan. Okay, example 4 takes us to the formulas for working out r sine, r cos, and r tan. Now, the original hyperbolic functions are all defined in terms of the exponential function e to the x. So it's not surprising that the inverse hyperbolic functions are defined in terms of the inverse of e to the x, natural logarithms. How are we going to prove this? Well, we'll start off with the definition of sine x, which is e to the x minus e to the minus x over 2. And then the normal method for working out an inverse function is rewriting the function so that we have x as a function of y. The way we'll do that is by creating a quadratic in e to the x and then using the quadratic formula. Okay, I'll let you have a go at working your way through all of that yourself. So pause the video, have a go, and then come back to me when you're ready. Okay, let's have a look. So that is the starting point. Now we want to rearrange this so that we can get x as a function of y. Moving the 2 across will give me that. Moving that term over here will give me that. And then, as is frequently the case with this form of equation, we're going to multiply through by e to the x. And the reason why we do that is we're going to get e to the x squared here. That'll become a constant. And here we've got 2y e to the x. Rearranging that does give us a quadratic equation in e to the x. And at this point, I can use the quadratic formula, which means that e to the x will equal minus b, which is 2y, plus or minus the square root of b squared minus 4ac, which will be 4y squared plus 4, all divided by 2a, which is just 2. Taking the 4 out of the square root will give me that. And then dividing by the 2 will give me that. Now then, we can't have a minus value here. And the reason why we can't have a minus value here is because if we had y minus the square root of y squared plus 1, that will give us a negative value for e to the x. But e to the x is always positive. So the consequence is we can only have the positive possibility here. We then take the logarithm of both sides. So the log of e to the x is equal to the log of the right-hand sides. And the reason for doing that is log and e cancel each other out. And at this point, we do have x written as a function of y. Now, that is the inverse function written in terms of y. It is more normal to write the function in terms of x. So all we do at this point is substitute x for y. And that gives us the inverse function of sin x is equal to the log of x plus the square root of x squared plus 1. Okay, example 5 is doing exactly the same thing for our cos x. So that's the equation for cos x, e to the x plus e to the minus x over 2. That's how it's defined. To find the inverse function, we need to write x as a function of y. Once again, we'll create a quadratic in e to the x and then use the quadratic formula. So it's very, very similar to the last example. There is an issue at the end to do with the pluses and minuses once we've used the quadratic formula, but we'll worry about that when we get there. So have a go yourself. Pause the video, see if you can work your way through this one, and then come back to me when you're ready. Okay, let's have a look. So that's the definition of cos x. Again, exactly the same as before, moving the 2 across, rearranging things, multiplying through by e to the x, tidying things up, and collecting the terms together till we have a quadratic in e to the x. And then using the quadratic formula, we will get that. Taking the 4 outside of the square root again gives us that. Dividing through by 2 will give us that. Now this time we'll press on before we worry about the plus and minus options. So taking the log of both sides gives me that, which means that x is equal to the log of y plus or minus the square root of y squared minus 1, which would be the inverse function. But now we do need to think about the plus and the minus. If you remember to the sketch of the inverse function, our cos x, we had to limit the domain, and the consequence of that was that our cos was always greater than or equal to 0. But for x greater than 1, which is how it's defined in the domain, x minus the square root of x squared minus 1 will be less than 1, and the log of a number which is less than 1 but greater than 0 is itself negative. And that's the inverse, but it can't be negative, because we said that our cos x has to be greater than or equal to 0. So for that reason, we only take the positive value. And the inverse of cos x is our cos equals the log of x plus the square root of x squared minus 1. So that's our sin x, that's our cos x. In a similar fashion, we can work out that our tan x is equal to a half log 1 plus x over 1 minus x, where the modulus of x has to be less than 1. And the last example, it's very straightforward. All we're going to do is just show how these formulas work. So we'll be expressing these as natural logarithms. So you're just getting the answer equals log something. All you have to do is substitute in 4x in the relevant formula. Very little is going on. But I'll let you have a go at them yourself. So pause the video, try and work these out, and then come back to me when you're ready. Okay, let's have a look. So first of all, we have r sin 2. Now, as I said, all we're going to do is use the formula for r sin x and substitute in x equals 2, which will give us that. And that tidies up to r sin 2 equals the log of 2 plus root 5. And you don't need to go any further. Question 2 is r cos 3. That's the formula for r cos. If we substitute in 3, we'll get that. And again, that tidies up to give us r cos 3 equals the log of 3 plus root 8. With our than a half, we can do a little bit more work with tidying things up. But first of all, substituting in x equals a half will give us that. The fraction simplifies to 3 over 2 over a half, and that simplifies to half log 3. Now this half we can incorporate into the natural logarithm by writing arc than a half is equal to the log of 3 to the power of a half, or log root 3. Okay, that does get us to the end of this lesson. If you've got the textbook, then turn to page 9 and have a go at exercise 1C. Thank you very much for listening, and cheerio.